Hello one and all, I am Dr. Lalitha, Assistant Professor, Department of Electrical and Electronics Engineering, MLR Institute of Technology, Hyderabad. So in today's video, I am going to explain about the most important topic in the electrical circuits, that is star to delta and delta to star transformation. So what is star, what is delta, how to transform from star to delta as well as delta to star will be explained in this video. So coming to star and delta. So what is a star and what is a delta? We all know that voltage will generate the voltage. Generation, transmission and distribution will take place and ultimately the voltage will come to our load. So while generating and transmitting and distributing will give so much of connections, a lot of connections, like we are going to convert from star to delta and delta to star. We are going to transform the voltages connection from star connection to delta connection and delta connection to star connection. That means the generated voltages will be transferred to the distribution through transmission with the help of the delta connection or star connection. So if we see here, see these three are resistors. So resistors or impedances, whatever it may be. So while transmitting, if we connect the R phase, Y phase and B phase, these three phases like this in this connection, then we'll call it as a delta connection. So this is a star connection. That means the R phase, Y phase and B phase, if we are connecting like this is called as star connection. So here, while we are transmitting the voltages, we are transmitting the voltage through phases with the help of delta or with the help of star, we are going to transform. So while we are using here, see here, this is one line, this is one line, this is one line. Here is one line, one line, one line. All these lines represents the phases. So R phase, Y phase, B phase, R phase, Y phase, B phase. So likewise, each phase will be connected in this manner. But here the thing is that if we connect these phases in terms of star, then neutral point will also exist here. Neutral point will also exist here. If we connect in the delta, there is no possibility of connecting the neutral here. So based upon this, while connecting the loads, there is a possibility of changing the delta to star or from star to delta conversions. Means in some cases or in some loads, star connection is sufficient, or in some loads, delta connection is sufficient. So in some cases, the situation will come where we need to transform from the star connection to delta connection or from delta connection to star conversion. So this conversion of changing from the star to delta and delta to star plays a major role in the electrical circuits, that too in the transmission of the electrical system. So in any electrical network, the impedances can be connected in various configurations. So these are the main configurations, these two configurations, star and delta configuration. And also star to delta conversion and delta to star conversion is very much useful in reducing the circuits. Means if there is any complex circuit, we can reduce or we can solve the circuit by using these conversions. So star to delta and delta to star plays a major role in the electrical circuits, in learning the electrical circuits and also in solving the complex problem. So now let us see about the star connected network. So what is a star connected network? So if the resistances or impedances, whatever it may be, so why here I am considering resistances and impedances means, so Z means R plus Jx. Z means R plus Jx. So Z is equals to R in the case of DC circuits, but in the presence of AC, X also will be there. So we can transfer AC as well as we can transfer DC, right? So that's why I am considering the impedance. Otherwise, if I treat that I was transferring only DC, then Z will become R because X value won't be present. So R plus 0, so Z is equals to R. So directly I can represent R. So if I represent impedance or if I represent resistance also, there is no problem. So based upon the supply which I am giving, we can use Z or R, whatever it may be. Both the equations or both the derivations will be same. If we consider R, then only we'll represent R in the circuit. If we consider the Z, we'll write down or we'll solve the equations with respect to Z. So the star connected network is formed when three branches or impedances are connected together. So see here, three branches. This is one branch, this is one branch and this is one branch. All three branches are connected together. Here there is a common point. See here, there is a common point and remaining other branches are free. So this type of connection is called as star connection. So this connection can also be rewritten or redrawn like this. See here, T-type network. The same network I'm representing like this. I'm reforming. This resistance is this resistance. This resistor is this resistance. This one is this one. So both are same. But for our convenience, we are converting from this network to this network. Both are same. Okay. So this connection is called star type of connection, where there is a possibility of connecting the neutral in this circuit. So during the transformation, we won't change any terminals, or we won't change any impedance or any other values. Just we should convert from delta to star or from star to delta. So now we had seen the star network. Now we will see the delta network also. So this is the delta network. So delta network will be in the form of this shape of delta or triangle. So this type of network is called as delta network, and this type of network is called as star network. So in some cases we'll convert from delta to star, and in some cases we'll convert from star to delta, because some of the connections will be given in the delta connection, some of the connections will be given in the star connection. So first, there will be derivations to convert from delta to star and star to delta. So let us see each in detail. So first one was delta to star conversion. So this delta connected network can be transformed into the star connected network with one particular formulas. Similarly, star also will be converted into delta with the help of some particular formulas. So we need to derive those formulas from the basic equations. Then these formula can be useful for reducing the electrical complex circuits. So see here, the total impedance between the A and B in the delta network. See here. So this is the delta network. This is the star network, right? Now I am converting from this network to this network. So while I am converting, see, I was keeping the terminals A, B and C. Here also I will keep the same terminals because the voltage and connections won't be changed. Only the thing is that these connections will be interchanged. That's it. From delta to star or star to delta. So A, B and C terminals are there. So these A, B, C and terminals are not changed. And these resistances are named in delta as R1, R2 and R3. Here in the star, we'll rename it as RA, RB and RC. Why I am differentiating here means, while we are sorting out, while we are changing from delta to star or from star to delta, if we keep the same values in star and delta, then we don't know whether it was related to star or it was related to delta. So for that sake, here in delta, I was naming it as R1, R2 and R3. And in the star, I was naming as RA, RB and RC for easy identification. So see here, the total impedance between A, B in the delta network. So A, B, see here, A, B in the delta network. So A, B, in A, B, what is there here? R1 is there. Okay. So see here, R1. So this, how this R1 is with other elements. So R1, these two are in series, that is in parallel with R1 here, right? So this R1 is parallel to this R2 plus R3. These two are connected in series. So that's why here we'll write the equation as R1 parallel to R2 plus R3. So just like resistors are connected in series and parallel, we'll use the same formulas. So in series connection means R1 plus R2. That means here we have R2 plus R3. So what is the equation when two resistors are connected in parallel? R1 R2 by R1 plus R2. Here the same I will apply here. So R1 parallel to R2 plus R3 means, what is the formula of resistors connected in series? R1 R2 by R1 plus R2. So R1 R2, first we will multiply this R1 into R2 plus R3 divided by R1 plus R2. This is R1, this is R2, right? So R1 plus R2 plus R3. So RAB is equals to R1 of R2 plus R3 by R1 plus R2 plus R3. Note down this as equation 1. Similarly, how we had done here, the same will be done for terminals BC as well as terminals AC. See here, if we are considering BC terminals, so across BC terminals, what is there here? R3 is there. So we have to consider R3. So R3 is how with remaining two values. So R3 is parallel to R1 plus R2. R3 is parallel to R1 plus R2 because these two are connected in series, but the value of R3 is parallel to R1 plus R2. So likewise, see here, R3 parallel to R1 plus R2. Again, these two are connected in parallel. So resistors connected in parallel means R1 R2 by R1 plus R2. So this is R1, this is R2. So R1 R2. So R3 into R1 plus R2 by R1 plus R2 plus R3. Note down this as equation 2. Similarly, AC. So AC. So how we will consider AC? In AC, what is the resistance value is there? R2. So R2 is parallel to R3 plus R1. R2 is parallel to R3 plus R1. Because while we are considering AC, so we have to consider with respect to R2. So R2 is how with respect to remaining two resistors. So R2 is parallel to R1 plus R3. So R2 is parallel to R1 plus R3. So similarly, we will apply the same formula here whenever the resistors are connected in parallel R1 R2 by R1 plus R2. So R1 R2 means R2 of R1 plus R3 by R1 plus R2 plus R3. So note down this as equation 1, 2 and 3. So now we had written the equations with respect to delta. So now we have to write down the equation with respect to star. Means see here. For this equation or for this delta network, I had written down these three equations, right? So now for this star network also we have to write down the equations. So why we need to write down separately? So while we are converting from star to delta, delta to star, we have to prove that both of them are equal. So for that we need to equalize those values and these values because the voltages or the values should not change in the circuit. Whenever we are interchanging from star to delta, delta to star, the values should not be changed. So that's why here we have to prove that both the values are equal and we have to derive the derivation from both the values. See here, according to the star network, here what are the terminals is there? See, RAB, RBC, RAC. So if we consider RAB, so in RAB what is there? RA is there, RB is there. So RAB is equals to RA plus RB. RBC is equals to RB plus RC. RCA is equals to RA plus RC. See. So, from the star network, we got these three values. From the delta network, we got the previous values. So, now what we have to do? We have to equalize both of them because we are proving that both of them are equal. So, RAB plus RBC plus RCA is equals to, what are the values? Previous values which we got? R1 of R2 plus R3 by R1 plus R2 plus R3 plus R3 of R1 plus R2 by R1 plus R2 plus R3. Similarly, R2 of R1 plus R3 by R1 plus R2 plus R3. So, I am adding the equation 1, 2 and 3 together. So, I am adding here, see. So, RAB. What is the value of RAB? We know that from the star network, RAB is equals to RA plus RB. So, I am substituting the value of RAB here because RAB is equals to RA plus RB. Similarly, RBC value means RB plus RC. So, RB plus RC. Similarly, RAC value means RA plus RC. RA plus RC is equals to, we are writing down those values. So, R1 plus R2 plus R3 is common here. R1 plus R2 plus R3 is common. I had taken common LCM. So, R1 of R2 plus R3 plus R3 of R1 plus R2 plus R2 of R1 plus R3. So, now if I am solving these values, here RA and RA is there 2 RA, RB and RB is there 2 RB, RA, RA, 2 RA, RB, RB, 2 RB, RC, RC, 2 RC. So, 2 RA plus 2 RB plus 2 RC is equals to, I am multiplying R1 R2 plus R1 R3 plus R3 R1 plus R3 R2 plus R2 of R1 means R1 R2 plus R2 R3 by R1 plus R2 plus R3. So, if we are reducing this equation, we will get the final value of RA plus RB plus RC is equals to R1 R2 plus R2 R3 plus R1 R3 by R1 plus R2 plus R3. So, note down this as equation 4 and keep it aside. So, now we have to subtract the equation 1, 2 and 3 one by one from the equation 4. So first subtract equation 2 from the equation 4. So what is equation 2? See, we are subtracting the values. Equation 2 is this one. Okay. Next, equation 4 is this one. So I am subtracting the equation 2 from equation 4. So if I am subtracting the values, then I will get the RA value. RA is equals to R1 R2 by R1 plus R2 plus R3. So similarly, if I subtract 1 and 3 from the 4, we will get RB and RC values. Okay. RB and RC values. So we got the equations of RA, RB and RC with respect to R1, R2 and R3. So RA means R1, R2 by R1 plus R2 plus R3. Next RB means R1, R3 by R1 plus R2 plus R3. RC means R2, R3 by R1 plus R2 plus R3. So note down these as equation 5, 6 and 7. So from RA, RB and RC, we got the values of R1, R2 and R3. So from the derived equations for star equivalent resistance, means RA and RB and RC, we can conclude that the relation between delta to star and the equivalent star impedance is equal to the product of adjacent delta impedances with a terminal divided by sum of 3 delta impedances. So these 3 are delta impedances, right? R1, R2 and R3. So these are consecutive impedances. Impedances or resistances, whatever we consider, the equations are same. If they asked us to write in terms of impedances, then you will replace it with Z. If they asked us in terms of resistances, you can write down simply with R. So next one was star to delta conversion. So previously we had converted from delta to star. Now we are converting from star to delta. So this is the star connection. This is the delta connection. So similarly what I had considered before, the same we are doing here. For in the star we are representing RA, RB and RC. In the delta we are representing R1, R2 and R3. And we are converting from this to this. Previously we convert from this to this. But now we are considering from this to this. Okay, so in order to find out the equivalent delta resistances, what we have to do was, we have to multiply the previous equation of equation 5 and 6 as well as equation 6 and 7 and 5 and 7 together. See here. 5, 6, 5, 7, these values which we got from these conversions, we have to use here in order to find out the values. So first what we have to do? We have to multiply the equation 5 and 6. We have to multiply the equation 6 and 7. Next 5 and 7. See. 5, 6, 5, 7, 6, 7. So we have to multiply all these values. So RA into RB is equals to, what is RA value? We have to see here. What is RA value? R1, R2 by R1 plus R2 plus R3. Okay. See, R1, R2 by R1 plus R2 plus R3. Up to here, this is RA value. Substitute RB value here. What is RB value here? RB means R1, R3 by R1 plus R2 plus R3. Substitute the value here. Multiply these two values. So, R1 square, R2, R3 by R1 plus R2 plus R3 whole square. So, this is equation 8. Similarly, multiply equation 6 and 7 and with 5 and 7. Means these two. If we multiply these values, we will get RBRC and RARC. RBRC is equals to R1, R2, R3 square by R1 plus R2 plus R3 square. Next, RARB is equals to R1. RARB is equals to R1, R2 square R3 by R1 plus R2 plus R3 whole square. So, note down this as equation 8, 9 and 10. So, now if we add equation 8, 9 and 10 together, then we will get, see here, we got here RARB, RBRC and RARC, right? If we add these three values, equation 8, equation 9 and equation 10, see RARB plus RBRC plus RARC is equals to LHS as well as RHS also. See here, R1 square R2 R3 by R1 plus R2 plus R3 whole square plus R1, R2, R3 square by R1 plus R2 plus R3 whole square plus R1, R2 square, R3 by R1 plus R2 plus R3 whole square. So I'm adding all these values. So and I'm taking LCM. So if I sort out this, finally we'll get RARB plus RBRC plus RARC is equals to R1, R2, R3 by R1 plus R2 plus R3, because here it will get cancelled, right? So finally we'll get R1, R2, R3 by R1 plus R2 plus R3. So in order to find out the equivalent delta impedance or resistance, we have to divide the equation number 11 with equation 5, 6 and 7. So from this 5, 6 and 7, then we'll get the individual value of resistances or impedances. So see here. So dividing the equations 11 with 5, dividing the equations 11 with 6 and 7 separately, we will get R3 is equals to RARB plus RBRC plus RA by RA, and R2 is equals to RARB plus RBRC plus RARC by RB, and R1 is equals to RARB plus RBRC plus RARC by RC. Means here everything we got with respect to R1, R2, R3 in LHS, and in RHS we got relation with respect to RA, RB and RC. That means there is a relation which is formed in between this delta and star. So if we solve these, if we sort out these equations R1, R2 and R3 equations, then it will finally gives rise to R1 is equals to RARB by RC plus RB plus RA, R2 is equals to RARC by RB plus RA plus RC, R3 is equals to RBRC by RA plus RB plus RC. So these are the final equations from which we will derive from delta to star conversion. Okay, delta to star conversion. So these equations, from all these equations we can convert from delta to star and star to delta. So these are the equations which are going to sort out the star to delta conversion. So from these equations, okay, we can easily convert from star to delta and delta to star conversions, so that it is very much useful in solving the complex circuits. So if they had given us very big circuits, in order to sort out those circuits by using like super mesh, super node, likewise if we are connecting if we are sorting out in a big way, then it will become complex problems. So by using this type of star to delta and delta to star transformations, it can be easily solvable. Thank you.